In recent months, the space probe Voyager 2, launched originally in 1977, became the second man-made object to escape from our solar system and begin its journey into interstellar space. We know it's done that because it's crossed the heliopause, a bubble made by particles, known as plasma, that stream off the sun and surround the solar system. To learn more, Adam Murphy spoke to Du Toit Strauss from Northwest University in South Africa.
So the sun basically continuously releases plasma. So as the solar atmosphere expands, it forms a supersonic solar wind that essentially blows past the planets into space. And this solar wind blows a bubble in the interstellar medium, which is called the heliopause.
And how did we know that Voyager 2 had gotten through it?
So for Voyager 1, it was, which happened a couple of years back, it crossed the heliopause, it was a little confusing. Voyager 1 did not have a working plasma instrument on board. So there was a lot of arguments to and fro, did we actually cross into interstellar space? For Voyager 2, it was a lot easier. So Voyager 2 still has a working plasma instrument on board, and we could actually see from the measurements the exact time where it stopped measuring solar plasma. So that's kind of the smoking gun indicating that we crossed into the interstellar medium.
And what happens now with Voyager 2? Is it still going to send back data, and what's that data going to tell us?
Yeah, so Voyager 1 and 2, they are still sending back data. What we really want to measure is we want to measure the interstellar medium. So we want to know what's the temperature, the density, the magnetic field of the interstellar medium outside of the heliosphere. So Voyager 1 and 2 will continue to do measurements for hopefully the next, maybe up to the next 10 years. And hopefully they can still send back data. So the big problem is they are powered by decaying radioactive material. And it's now 42 years, so it's not producing enough power anymore to power all the instruments. So they're starting to do fancy energy cycling or power cycling, where you're switching off some instruments and switching on other instruments in order to extend the life of the spacecraft as far as possible.
And just to give people kind of some idea of context, how far away is Voyager now?
Yeah, it's really difficult to explain to someone exactly how far they are. So we work in a unit called astronomical units, which is the average distance between the Earth and the Sun. So 1 AU is the average Sun-Earth distance, and that's about 1.5 billion kilometers. Voyager 2 crossed the heliopause at 120 AU. So that's so far that signals sent to the spacecraft or signals or data coming back from the spacecraft takes about something like 18 hours to reach us, moving at the speed of light. So it's pretty far away.
What do you reckon the importance of Voyager 2 as a mission has been and will continue to be?
I mean, since they've been launched, I think they've been trail-breaking missions. So they were the first spacecraft to photograph the planets. So the Uranus, Venus, they did all the planetary flybys. And of course, they switched off the cameras when they passed the outer planets. And this whole Voyager interstellar mission wasn't part of the original program. So this is kind of like a very neat add-on that we had onto the original mission. They are probably, for the foreseeable future, the only spacecraft we have that sampled the outer heliosphere, and definitely, as far as I know, they're going to be the only spacecraft for the next 10 or 20 years that will reach the interstellar medium. There's no other way to sample it. I mean, it really takes 42 years to reach those distances.
Du Toit Strauss speaking with Adam Murphy. That work has just been published in Nature Astronomy.